Hello everyone, let's go ahead and take a look at differentiable functions. Now we've already gone ahead and studied the derivative, how to find the derivative function, and also how to find the derivative at a particular point using limits. So before we go ahead and take a look at some of the results that we have in this section, let's go ahead and just review what those two are. So here's the definition of the derivative. It's f prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. And of course that function exists so long as the limit exists. Now the derivative at a point x is equal to c, we use this particular formula, and that's f prime of c is equal to the limit as x approaches c of f of x minus f of c divided by x minus c, which implies, assuming that this exists, that the limits as x approaches c from the right and from the left are the same, exist and are the same. Okay, so we wanted to go ahead before to take a look at where the derivative, what the derivative was at a particular point, or find the derivative of the function. Now what we want to do as well is we want to take a look at where the derivative does not exist. And it doesn't exist at these 3 points. Points of discontinuity, cusps, and vertical tangencies. So let's take a look. If we go ahead and take a look at 1, which is points of discontinuity, and let's say I have this explicitly defined function, f of x, and it's going to be equal to 1.5, x is greater than 0, and it's going to be equal to 1 if x is less than or equal to 0. Now, if we go ahead and take a look at the graph, this is what the graph would look like. Now what we're trying to do is we're trying to determine whether or not the derivative actually exists at x is equal to 0. Now if we go ahead and take a look at using the derivative at a point formula, I need to go ahead and determine whether or not, if I approach 0 from the left and from the right, the derivative will actually come out to be exactly the same, or the gradient will be exactly the same. Now what happens then is that if I go ahead and substitute f of x and f of 0, notice that f of 0 is going to be equal to 1, and f of x as we approach from the left is also going to be equal to 1. So what I'm going to have then is 1 minus 1, which is of course 0, and 0 divided by any small negative value is still going to be 0. But if I go ahead and approach it from the right hand side, the limit as x approaches 0 from the right, it's going to be slightly different because the function is different. The function now is actually 1.5. So at 1.5 minus 1, divided by, again, a very small positive number in this case, and being that I have 0.5 divided by a very small number, that of course is going to go to infinity. So what happens now is that I know that 0 is not going to be equal to infinity, of course, and therefore the derivative does not exist at x is equal to 0 for this particular function. Okay, let's take a look at cusp. Now, what exactly is a cusp? A cusp is a very, very sharp turning point, and usually we're associated with the absolute value function when x is equal to 0. So if you have a v, then that sharp turn like that is going to be considered a cusp. So here again is my function f of x equal to the absolute value of x, rewritten explicitly, and this is what it looks like. Graphically, this is what we have. Now again, if I go through the same process to try to determine whether or not the gradient exists at x is equal to 0, I go ahead and use the derivative at a point formulas, and I approach that particular point in question from both the left and the right hand side. Now if I go ahead and substitute f of x as x approaches 0 from the left, notice that what I'm doing is I'm using this particular function, the opposite of x. So the opposite of x minus 0 divided by x, of course that's going to give me a negative 1. The limit as x approaches 0 from the right is going to give me x minus 0 divided by x, which of course is going to be equal to 1. Now we know that 1 and negative 1 are of course not equal, and therefore the derivative does not exist at x is equal to 0 for the function absolute value of x. Now of course this hopefully should make sense, because if I'm approaching 0 from the left, this way, the gradient is negative 1, whereas the gradient on this side over here is 1. So when we get to the point 0, what exactly is the gradient? It cannot be two things at one time, and so therefore we say it doesn't exist. Okay, let's take a look at number 3. These are vertical tangencies. Now, I'm going to use this function, f of x is equal to x to the 1/3 power. That's the graph. And again, we're going to focus on the value of x is equal to 0. So if I use the same process that we have as we've done before, notice that what I'm going to come up with for both sides is I'm going to come up with 1 over x to the 2/3. As I'm approaching from the left of 0, and as I'm approaching from the right of 0, notice that from the left I'm going to come up with a negative infinity value, and from the right I'm going to come up with a positive infinity value. So of course those two are not equal, and therefore you do not have a gradient value at x is equal to 0 for this particular function f of x equals x to the 1/3. Now we could have actually have done this a little bit differently. We could have said that f prime of x is just going to be equal to 1/3 x to the negative 2/3 by using the power rule. And just by looking at that function, we know that x cannot be equal to 0, so the derivative cannot exist at 0, and therefore we come up with the same result if we approach it from a different way. Now the one thing that we want to go ahead and take a look at that's a very, very important part of this particular section is this statement right over here. If f of x is differentiable, then it's going to be continuous. Okay, that's going to be a true statement. But the opposite, or I shouldn't say the opposite, sorry, the converse of that statement, which is if f of x is continuous, therefore it is differentiable, is absolutely false. And we've gone ahead and taken a look at that. Now this one, of course, doesn't apply, but this one and this one both do. And x is equal to 0, the function is continuous, but it is not differentiable. Even at this case over here, the function is definitely going to be continuous, but it is not differentiable at x is equal to 0. Okay, so let's wrap up. Again, we're talking about differentiable functions. We looked at how to take the derivative or find a derivative function and find a derivative at a point x is equal to c, which is going to help us to determine whether or not the derivative exists at a certain point. And we know now that at these points of discontinuity, at cusp points or at vertical tangencies, your derivative will not exist. And algebraically, that's the way that we go about doing it. Now we also need to go ahead and keep this in mind, that if f is differentiable, f of x is differentiable, it's going to be continuous. But if it is continuous, you cannot assume that it is differentiable. Okay, so we'll go ahead and take a look at more examples in class the next time that we meet, and we'll take any questions that you might have then about this particular video. See you then. Bye-bye.